if you want to squeeze it on there, it's fine, but yeah, separate sheet would be better. You get the back of the paper. So I try to be really specific because I chapter 1.
What is the difference? Are you doing this? Is what just like quality of it, what was quantity is the number. So I can see the sexual surgery offered on the example of that. There's what the true value of what we're trying to get. We should expand the value. What?
Because I had no calculator.
Oh, how do you calculate?
What'd you say? Okay, it's your mental value. Minus your sales value.
Alright guys, answer the last one you're answering for now, and then we can kind of chat about some of these, because I think you guys will know some of the stuff at the bottom. The one with about the 6-big calculations, you didn't even touch in the video last night, so I knew that was going to be a stretch. But it is on your lecture note sheet that I gave you already in the folder. Take like 30 more seconds for everything.
Smart board.
Alright guys, if you guys can talk about I'm going to go down to the accuracy and precision one, number 2. Talk about a scenario where you would consider, or where you could explain something that would be accurate versus something that's precise. So talking to your groups for a second, I'll have one person share. A scenario, like a real life scenario where something would be considered accurate and or precise. All right, raise your hand if you have an awesome example. I'm ready. Raise your hand. Oh, gosh, all of your hands are raised. Oh, okay, so let's go. Who plays baseball? Softball? Golf? Football? Track? Band? Tennis? What am I missing? Lots of things. Swimming? Oh, you guys are just great this morning. Okay, so there's a lot of things in sports that I would consider would be a good example of how would you consider something to be accurate or precise. So in softball, what would be the accurate value or thing you were trying to achieve? The goal of everyone in softball or baseball. And home run, baby, right? You want a home run. So accurate would be you want that home run. Okay? So you want it to go straight over center field head, it's gone, right over the fence. What would be a precise value would be if you kept fouling the ball, you know, foul, 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 off the left field, third base, maybe 10 or 15 times. Okay, eventually you'd be out. But you'd be really precise if you did it 15 times, right? But are you accurate? No, because the accurate is the home run. You're rounding the bases, you're gone. So precise is that you are really able to reproduce the value or whatever you are doing over and over and over again. But is precise accurate? Yay or nay? No. If you are accurate, are you also precise? You can be. If you hit the accurate value or whatever it is that you're considering as accurate, if you do that numerous times, that's reproducing the accurate value, right? So you can be accurate and precise, but sometimes you can be precise but not accurate. Okay, do you guys feel you have a decent understanding of the accuracy precision debate here? Okay, so if you're shooting a basketball, swoosh, 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 you got it accurate. If you hit that left side of the backboard over and over and over again, you are so precise, but you are not accurate. Okay, so I think that that's pretty easy to understand at first. Quantitative and qualitative, you guys probably have a good wrap on. So the percent error calculation. Let's just think about in general. Do you always, whenever you're doing measurements, whenever you're in the lab, do you want a lot of error? No. Okay, so what would be a good percent error if you were a good, awesome lab person? What would be a good amount of percent error? Shout out a number. 2% error, 3% error, 15% error. That's still pretty, you're still pretty close. If you look 1,000% error, something has gone very, very wrong. So you generally want low percent error. And then in terms of like, what do these values actually mean? You'll see me write it a couple different ways. Accepted or actual, minus experimental, and this is absolute value. Okay, so it doesn't matter if you do A minus E or E minus A, it's absolute value. It's always a positive value and express your percents. So actual minus experimental over actual times 100. So we'll do an example with that, and you guys did one in your video. So if I had, let's say I had a device and I was measuring how tall I was, and I am 5'7", okay, and that's my actual height. So how many inches is 5'7"? 67 inches, thank you. That's my actual height. And Frank measures me with a weird ruler. Yardstick doesn't work all the way. And he gets 60 inches. So just 5 feet. I'm like here. So 60 inches would be the experimental value that you achieved in the lab, not in a standard setting. And so that would be my experimental. When I divide by my 67 inches, which was my true or approved value that was considered actual, how would I get percent error? I'd have to do what first? Do your PEMDAS, right? So 67 minus 60 is 7. What's 7 over 60? 7 divided by 60, sorry. Oh, 60. I got you. I was like, why are you saying 67 over and over? Okay. Do you guys have calculators? You know, I'll pass this little bucket around. Here. Pass the bucket around. Please get out a calculator if you have one. Anybody? What's funny? Oh, sorry. 0.1. 3 times 100. 10.4. Okay. So Meredith said 10.4. She took the 7 divided by 67. And I will go ahead and note a couple of ideas about significant figures here. Eventually, we're going to learn about how do you implement significant figures in our calculations here. But soon, that'll be today, we'll get there. But at this point, I'm going to go ahead and tell you, you only need one significant figure in this number. Well, how do you take 10.4 to one significant figure? We'll kind of get there, but I would just put 10 with no decimal, 10%, and that would be my percent error. So would Frank be a good lab partner if you got 10% error? I mean, I'd take it, right? It's not that bad. He'd be right there. All right, does everybody have a calculator who needs one right now? We might have to pass them over to share, but we'll get there. Okay, so keep on going here. I'm going to skip the significant figures for a second. Go to number 5. This row, give me two SI units. Just 2. Grams, and that's going to be used for mass. What else? Liters, and that's going to be used for general volume. I'll come back. Give me 2 more from this group here. We said grams and liters. Moles. We'll eventually get to what a mole is, and that's going to be generally a very specific for chemistry. What else? Say again? Kilos is going to be the prefix you can use. I want to hear like an actual SI unit first, and then we'll jump into the prefixes. So kilometers maybe, okay? Kilometers is another way to say it. So that's going to be more about length. Seconds is another one. Some more from this group, from this table. Degrees Celsius. Now, degrees Celsius is one way, and there's another way that we can express temperature. Kelvin. Okay, so while we're on the temperature side of things, the absolute, number 9, the absolute temperature scale uses which of those units? Shout it out. Kelvin, right? So I'm good with you guys giving me some oral answers here. So Kelvin is a way that we actually express our units of temperature across the globe, and it's important that we all talk about units in the same sense because there was actually an accident at NASA. They had some engineers do some calculations with their fuel tanks, trying to figure out how much fuel they needed to get where they're going, and they didn't use the same units across all the engineers, and so there was actually I think a minor explosion that occurred because they didn't have the consistency of their units, and so they thought they were all doing the same way, but they didn't. So there is a global system called a system of our international system of units, SI units, that we generally use. What is absolute zero? 0 Kelvin, but what is that in Celsius? That's not okay. That's 0 Kelvin, okay? Negative 273 Celsius because the difference between Kelvin and Celsius is just an addition or subtraction of 273.15 or 273. And then, so if you were to convert something, you would need to add your Kelvin, your 273 to become Kelvin. So if we're at room temperature, keep going, scooching around here. Room temperature, what is the temperature of room temperature? 25 Celsius, awesome. Okay, so how would I take that to Kelvin? Add 273, and what is that in Kelvin? 298 Kelvin. Beautiful. Okay, so you'll see that often. We won't do it a whole lot right now, but we really will in our next couple units of study. And then question 12. I know we probably understand what a unit is now. It's going to be what we always write after a number. But why do we have these? Anybody want to have a theoretical discussion on why the heck do we even talk about units? Yeah, go first, Aaron.
You just like to make sure everyone, when you're like doing things like the NASA experiment, that everyone's on the same track.
Okay.
That way the measurements they can't affect the end result of the experiment or whatever.
Right, and it helps give some clarity and some context to what you're doing. So if I go, Brandon, I need 9 sodium chloride back there. He's like, 9 what, lady? 9 feet of it, 9 grams of it, 9 liters of it. It helps us really understand what we're talking about if we can mention things in terms of their units, because we have lots of units that express length, volume, mass, temperature, time. Like all the units express something totally different. So we have to make sure there are no naked numbers running around. Never naked numbers. They always have to have a unit on them. And so that kind of hits that number 12 for us. So I think that probably the hardest thing on your video last night was, what the heck is a significant figure? Would you guys agree? Were there some other things that were maybe fuzzy? Was a lot of it common knowledge, or I guess common knowledge for you guys at this point? I'll do a quick recap of our prefixes before I do that, and then we'll hit significant figures. So I know you guys know how King Henry died. How did he die? King Henry died by drinking chocolate milk. Now that's our basic system of our prefixes, right? And this is all based on the metric scale with zeros being our placeholders to basically give us a scale of the size of a number. So kilo means big, milli means small, and so that's just a scale size difference. So past the milli, I gave you 3 more prefixes. And I told you these dots were placeholders, right? So King Henry died by drinking chocolate milk, dot, micro. It's that funny looking U thing. Okay, it's mu, I think, in Greek. So dot micro, dot nano, dot pico. And then we will do one. Did I do mega? Okay, dot mega. So you will have mega in our next unit. So there's a broad list of prefixes that we can use. And so as you compare things, you always have to think about them as the differences of their spacing, which is zeros. Base, B here, base, it's going to be liter, meter, and gram. Notice that those don't have any prefixes as a descriptor on them. So if I was going to write milliliter, I'd go with the M here, ml. If I was going to put nanoliter like that. So that's how you change from your base unit to your individuals. But there's a difference in like their scale here. So if I said I have 1 liter, how many milliliters is equal to 1 liter? So it's a correlation here, right? So if I have to look at the difference in spacing, I'm here at base. Liter gets the 1 because it's the bigger unit. How many millis are in a liter? There's a difference of 1, 2, 3 zeros there. So what's the scale difference? 1,000, right? That's equal to 1,000 milliliters. 1 liter is equal to how many, nano liters? So what's the difference in zeros here? Can you guys count? 1, so I'm looking 1, 2, 3. The dots count. 4, 5, 6, 7, 8, 9. I'm not writing 9 zeros. That's not smart word. 10 to the 9th is how I'll write that. That's 1 billion, right? Something like that. Okay. And that's how many nanoliters, 10 to the 9th nanoliters in 1 liter. And what you should kind of think about is like, does that make sense? Does it make sense to have a lot of a teeny tiny unit in 1 big liter? It does. Like, you should have a bunch of little teeny tiny nanoliters in a liter. You should have 1,000 milliliters in a liter. So always make sure it makes sense to make sure you do it the right way. And we will work with those quite a bit in the future. Alright, so sig figs now, okay? So, before I do the practice problems with this, I think it makes sense to give you the idea of how, when and why do we use sig figs. Significant figures are just basically a way for us to talk about our measurements without being big fat liars, okay? So if I have a ruler that has lots and lots and lots and lots of little graduations, I can be very, very accurate with my numbers. So I can say, oh, my tape dispenser is 5.000 inches long, or meters long, or whatever, not meters, centimeters long. So I can be very accurate by giving you lots of numbers with it. But if I say, if I have a really crappy ruler and it's got like 1 or 2 little lines or inches or any graduations on it, I might say, this is only 5. Even though it's not very accurate, I'm going to just say 5. So the number of digits you give me gives me accuracy to it. So to kind of start you off, we'll take maybe 10, 15 minutes here, no, a full 20. And I want you guys to work through using this as a reference point to talk about some of these examples together. Not examples, I think that should work. There should be enough for everybody. Close here, I think I have some extras on the side over here. So start on the first part with the rulers. It says significant figures, significant digits and measurements. Is that correct? Starting on number 1, not 16. This is the one I'll need to eventually. You have the experiments. I'm trying to get my colors separate. So as you're probably reading the first part says why. Scientists do a lot of measuring. Scientists do a lot of measuring. When scientists use an instrument such as a ruler, guide, plate, cylinder, spectrophotometer, or balance to measure something, it's important to take full advantage of the instrument. However, they can't cheat and record a better measurement than the instrument is capable of, meaning graduations that are present here. There's an understanding among the scientists that a proper way to record valid measurements from any instrument, and that's in your significant figure kind of idea. When you are a scientist, you must record data in this way. When you are reading from other scientists, you must assume they have recorded their data in this way. So that's kind of what you're reading, you're kind of starting with here. Okay, so you guys do model 1 and 2. I know the first one's an awkward question. You're like, what is this actually asking? Anybody want to help me out on number 1 so far? What can you be absolutely certain of for this ruler with this object? Brandon. Right, that's it. This is a really crappy ruler. I would never ever want to use this ruler in my life because it's horrible. There are no graduations here for me to actually see the differences. But what can you be certain of? I know that this little gray block is more than 0 centimeters, but less than 10. That's all I know. I can't say, oh, I think it's about blank, because I don't really know. So now you can continue kind of with that in mind.
help each other out too.
Pause where you are for a second. I like to kind of give you a couple minutes to kind of get ahead, and then we'll kind of check and then jump back in. So I'm just going to use my little cards to call on you guys here. So first off, we already said the ruler was pretty horrible. Question 2, 6 students measure. Were they all able to agree? Ashton, what do you say?
I said no.
No, because you can see that they're all up here with 2, 3, 3 and a quarter, 3.33. They weren't able to agree because the ruler was just absolutely horrendous. Ruler in model 1 is not very useful, but they can estimate. What were some of their estimates, or how do they achieve what they did achieve? Megan.
They could have like looked at it from 1 to 10 and just like blocked it out by like centimeters if they are.
Right, so they maybe broke it in. I think they kind of broke it into like 3s or 4s, right? So they said, oh, it's about a third of the way, or maybe they broke it into quarters, and they said that's what they had to do, right? So they made it work, but it wasn't perfect, and there was no consistency amongst their measurements. Question 4, which is the next model here. Now, look, this is getting a little bit better. Look, we've got some graduations here. We actually have some true lines. So this is they obtained a better ruler. What distances can you be sure of, Avery?
1 to 10 centimeters.
And exactly like 1, 2, right? So, but you can be exactly sure of not only 1 through 10, but the numbers that go along with it. So 1, 2, 3, 4, 5, right? So we can see that for sure. So were they able to agree, Irie, on any of these values? Were they able to agree on any digit? Look at these people. We're in model 2. Were they able to agree on any of the digits, the 1's place, 10's place, etc.?
3.2.
So 3 is on here first, right? So you see the 3.2, the 3.1, the 3.3, and so forth. They were able to agree on the 3, right? So that gave us some consistency, and we're like, okay, this instrument is better. The instrument we're using, in this case, this better ruler, was able to allow us all to agree on 1 digit, and then we had to do, one second, you'll notice that Susan, Maya, all these guys, they had to estimate that last digit, right? So they all said, it's 3 point something, but then they all had some creative abilities to go 3.2, or 1, or 3, or 2.5, or 2.0. Now, what you're seeing is, though, Susan, Maya, and Jonah all estimated 1 digit past, and then Emily and Diane, they got a little high and mighty on us, and they're like, I can estimate 2 digits past what I know, but you can't. The rule is you cannot estimate more than 1 digit, and that keeps us all consistent in our number of significant figures we write down. And Tony, he just gave up. He's like, I think it's 3, but I'm not going to go any further. Tony basically lied, said it's 3. We all know it's not 3. It's more than 3. It's obvious, right? And then that's why these 2 guys are out of line as well, because they're estimating further than we're supposed to. So you'll start to see some consistency coming up here. Question 6. Oh, well, I think we kind of covered that. Let's come back. So question 7. There will always be uncertainty in measurement. This causes variation in measurements even if people use the same instrument. Compare the variation in measurements made. Which ruler resulted in greater variation? Which one resulted in greater variation, guys? 1 or 2? 1 for sure, because we didn't have very many graduations. All right, now look at model 3. Some of you guys may have gotten this far. Even better, we actually have little lines between the numbers. And so this is going to allow us, and as you might see in the measurements over here, we're allowed even more accuracy, and more accuracy the better our instruments get. And so this ruler, it's not one that you're probably going to get at the dollar store. So it's a nice ruler. We got some lines here. So what you're seeing is they are able to agree not only on the first number, but also what, Bradley?
On the second number.
Right. So you see 3.2 basically for everybody. That means there are 2 significant figures that are exact. They are absolutely sure it is 3.2 right there. But here's the thing. If you know exact, you don't stop at exact. You always have everybody in the world, when they do this, you have to estimate 1 further. Because this ruler is accurate to 2 sig figs, 3.2. But then it's between the 2 and the 3 parts. So you're like, I gotta make a choice here. So Susan and Maya, Jonah, they're all in good shape. They took that to 1 extra significant figure, though they didn't agree. They were all doing their job of making that estimated digit happen. Mark gave up. He said 3.2, that's all I know, but he truly needs to estimate one further. And again, Emily and Diane, they both didn't follow the sig fig rules. They estimated 2 further, which that means they're liars. They're telling us that they're super accurate when they are actually not. So far, you guys kind of seeing the theme here? What are some rules so far? Yeah. Right, that's pretty much the rule we've distinguished. 1, get a good ruler or get a good instrument. The more graduations on your instrument, the more accurate you are. The more accurate you are, the more digits you can kind of see that are being recorded. And the rule is that you can only go 1 digit past your estimated digit. 1 digit past your exact digit. We call that estimated digit the last one that we actually record. So using that logic, go down. I'm going to go to number 16. Actually, I lied, 15. Go ahead and discuss what you would record for this ruler on number 15. Take like 30 seconds here. Bradley, did you want to answer that?
No, I just had a question.
Yeah.
So what counts as an agreement? Does it have to be between 4 people who are measuring it? Or could it just be between 2?
Usually it would have to be between, hopefully everyone who's, what this was supposed to demonstrate that is that some people record willy-nilly numbers they want to because they're not following the SIG rules. So what you would see is that they're agreeing and they're following the rules. So it would have to be between the people that are actually following the rules. Okay, we'll get to more practice of that. Frank, help me out here.
7.0.
Okay, so he said 1, 2, 3, 4, 5, 6, 7. And so since 7 is the exact that he's saying, and he has to estimate one further, he said 7.0, right on the spot. Now, did anybody record anything differently? Maybe it's hard to see, and you said, oh, it's not quite 7. So I didn't know if somebody said 6.9, okay, because it's a little bit less. Or if it was a little farther, maybe 7.1. But notice, how many digits did I say that whole time? 2, 7 point something or 6 point something. Nothing like, oh guys, I'm super awesome, 6.9999999. No, because I don't even have any lines between there to give me that kind of accuracy. Question?
For the last model, or model 3, we have like 3.2 models. Did you say that it was 2 sig figs?
Back up here.
Yeah.
They should record 3 sig figs. 2 that are accurate, because you'll notice it's 3.2, but then the estimated one is our third one. So yeah, these guys up here, Susan, Maya, and Jonah, are all in a good place. They estimated one passed. Even though they didn't all agree on exact, that's where that uncertainty measurement comes in, just a teeny bit. All right, so down to 16 now, if I'm there. Looking at this one, and I blow this up just a little bit more. Discuss and let's come to a conclusion on what this one would measure. William, what do you think?
I still think 7.0.
Okay, sorry. William. Yeah, my bad. William. So you say 7.0, but look at our ruler. It has changed, right? Sure. 00 is better because that tells me, I know for sure you were like, okay, spot on. It's on the line. 7.0 is exact. But then he said 7.00 centimeters or whatever. Yeah, centimeters would be, that last digit would be the estimated one. Maybe Omar's like, I don't know, 7.02. But notice we're still estimating that last digit, nothing before, and nothing past to make us more accurate than we truly are. Just kind of keeps us truthful about our accuracy. Okay? So that's how we do it within the lab setting. Let's do it with some practice problems that you have on your lecture notes. These are the ones you took last night that you actually have a paper that I copied for you. It says like Unit 1 lecture notes or Honors Chem lecture notes. Find those for me. And I'm going to scoot you ahead past the notes you guys took last night. Alright, so Pacific and Atlantic method. You have to know where the Pacific Ocean is and where the Atlantic Ocean is. I know it's not geography, but I know you guys know Pacific and Atlantic because here we are, right there someplace. So my rules for that was basically learning that if you have a decimal present, you start counting significant digits from the Pacific, what did I say, present Pacific. If you have a decimal absent, meaning like, which of these would have an absent decimal? C right here. You would start counting sig figs from the Atlantic, meaning the right-hand side of that number. The zeros are misleading, so sometimes if you start off with a 0, you have to skip it because it's just a placeholder to tell you the size of the number. It's not a significant digit. And occasionally they are significant digits, so that's kind of where we get into trouble. So I'm going to actually start down here on D and so forth. So I want you guys to kind of give me the rules and like the steps you took to solve for this one. So if I'm on F here, the rule is you start where? Okay, so we're seeing the decimal is present. We see it right there. It's present. You start counting sig figs from the Pacific, which is this side. Whenever I'm going up a number from the left, what do I do with this 0? Don't count it. It is a leading 0. You start counting sig figs at the first non-zero digit. Okay, how about this 0? Skip it. Okay, so where do I start counting sig figs? 5. Okay, so 1, 2, 3. There are 3 sig figs there. Boom, boom, boom. That's it. That's still pretty accurate. How many sig figs, or I'm sorry, G. How do I count with G? Start from the Atlantic. You don't see a decimal there, right? No decimal. You start from the Atlantic. And so I'm coming in from the right. What do I do with these zeros? Skip, skip, because I have to start counting the first non-zero digit. So the only 2 I count are there, 4 and the 3. So there are 2 sig figs there. How about I? So, hold on. Do you see the decimal? Okay, this is a stealthy ninja back here. You got to watch for the decimals at the very end because sometimes that's a trailing 0, but it's actually an important 0, so we have a decimal there. So that decimal is present. So I start from the Pacific, present Pacific. Okay, so from the left. So then you're going to start counting at the 4, and once you stop, you don't stop. I mean, once you start, you don't stop, like Pringles, right? Once you open them, you can't stop. So 1, 2, 3, 4. 4 sig figs. So, which of these values is most accurate? Or most precise, really? The last one. The most digits means that it's a very accurate number. Give me a thumbs up if you could do that, just counting sig figs. It's okay, I just want to get a quick temperature of the room here. All right, so I'm going to use that a lot. I'm going to use that kind of vocabulary of Pacific and Atlantic a lot as we go. So, you guys did these for practice. Let's go ahead and just out loud tell me how many sig figs you got for these, okay? So, A. I hear 4. Okay, so we see no decimal. Decimal is absent. Start from the Atlantic. Do I count that 0? Nope. I skip it and move on. Okay, so there are 4 sig figs there. Let me get a different marker. 4 sig figs. Next one? 2. Okay, this one is also absent. Start from the Atlantic. Skip, skip. The 5 and the 1 are the only 2 that are considered significant figures. Next. G. I'm sorry, I'm going down this weird alphabet here. A, D, G. 1 sig fig, so you start from the Atlantic again because it's absent. Skip, 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 skip. Count. 1 sig fig. Next. 3 sig figs. That one's pretty easy. You see that the decimal is present. You start from the Pacific, skip that first leading 0. Count, count, count. Next. 1, because these are all leading zeros from the Pacific side. Skip until you meet the 8. 1 sig fig. Next. 2 sig figs. Great. You're seeing the decimal is absent. You start from the Atlantic, skip that first 0. Next. 4. Next. Say again. Okay, I thought I heard a 6 out there. So this one actually is 2 because you see the decimal is present. You start from the Pacific, but you do not count those until you have met the 5 and the 6 when you're kind of coming in there. So 2 sig figs. Next. 5, good, because this one has a decimal present. You start from the Pacific, so once you start counting that 2, you do continue counting. Next, 4, because that decimal's on the back side, so you do have to actually count those because you're starting from the Pacific and then to the right. Next, 4, because you have a leading 0, which you actually skip there. So you're going to start from the Pacific and then keep going. So those trailing zeros actually are accounted for because they do matter because we started counting. Next, 2 sig figs. Awesome. That one's not hard. All right, so we're going to use that and identify sig figs present because we're going to start adding, subtracting, multiplying, dividing with them. So it's important to know the rules of how do you actually count them first. Yes, ma'am.
How did you get 4 sig figs for H?
For H. Where's H? Okay. So here, the decimal is present, right? So if I see that it's present, I'm going to start from the Pacific over here. And once I start counting sig figs, I don't stop. So that 2 is my first non-zero digit. So I'm going to count, 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 count. And all of those matter. The stuff in the middle, I know they're zeros, but they're there to tell us the size of the number, so they are accounted for. So I always just use the Pacific Atlantic rule, and if you understand that, guys, then you'll be doing really well. So let's do some calculations with these. Before I do calculations, let me show you how to round. I know you know how to round. I know you do. This is on your paper, right? Double check where, so like the middle on the left side. So I know you know how to round, but sometimes when you have to round to sig figs, using appropriate sig figs, you actually cannot record the entire number, and you actually have to use scientific notation sometimes. So that's kind of why you watched that with scientific notation last night. So this is a big number, 50,600, right? Pretty big number. Yeah, there's some more there. It's very accurate 'cause it's got a lot of decimals as well. But if I only want you to record this with one significant figure, and I just put 5 and 50,000, that's totally off, right? I can't round 50,000 to 5. That's not even close to the number. So remember, when you're rounding, no matter the sig figs that are present or not, the number still has to be the size of the number. It's just you're going to modify how you write it. So how can I write this with one significant figure? Say again?
50,000.
Just 50,000. I'm still going to put all the zeros there as placeholders. And I know most of you guys are like, oh, but the 6 is there. I should round it up to 51,000, right? Yes, that's a true statement. But that's not going to be two, sorry, that won't be one sig fig. That will be two sig figs. So that's where you have to drop that down to a 0. So I can write 50,000 like this, and then milliliters. Oops, milliliters. And that is still the scale of the number, appropriate, but it's got one significant figure in it. So I can't lie by putting more than one sig fig if that's a requirement of the device. So the little reading up here kind of gives you some instructions on how do you round. But generally, you always start from the left with these whenever you're rounding, because most of the time we'll do some calculation. We'll get our calculator and have like 10 digits there. You're like, how many of these actually matter? So that's what I'm talking about. After you've done a calculation and you're looking at that number, you're like, what do I write down? You'll have to round it to the appropriate sig figs, and we'll kind of get to that in a second as well. But we're just working with rounding first. So whenever you're talking about the zeros present, you're indicating the zeros in this matter. You see there's no decimals. The zeros are there as placeholders. They're not actually significant digits. That's why I can say this is one sig fig. And there are instructions on page 66 in your book. So let's go down to 2 sig figs. What you have to do is, starting from the left right here, okay? You're going to go into the number 2 sig figs, and if those 2 sig figs or those 2 digits come down here, so if I put 50 down here, you do have to consider the next digit and say, does that next digit that I'm getting ready to knock out and put as 0, does that need to be rounded? So if I'm looking here, I see that 6. Does that 6 influence my 0? Yes, it means it's going to go up. So I'm going to erase that 0 and put a 1 there. And then after that, everything else becomes a 0 because it's just simply a placeholder to give me the scale of the number that I'm requiring. So I'm going to say that 6 is booted out. It's been accounted for. And now at this point, I have written that measurement as 2 sig figs. Notice how similar these numbers are, but now that I've gone into the number a little bit more, I could actually implement the 6 rounding nature. Yes, ma'am? No, because actually if I do that, that changes the accuracy of this number. That actually has 5 sig figs now. Okay, so when I exclude it, it actually does me good for my requirement of 2 sig figs. Okay. Okay, let's go down to I'm trying to see which one's harder. Yeah, let's go down to 4 sig figs. Okay, so I know you're going to look at the first 4 digits, right? So let's just write the first 4 digits, 5060. Is that number the same or even close to that number? No, we got 5,000, we got 50,000, not even close. So I could put another 0 here, and it would be 50,000, right? How many sig figs are in this number the way I have written? 3. Good, because first I see no decimals present, right? So it's absent. Start from the Atlantic, scooch, scooch, you're skipping those. And it would only be those 3 right there. That would actually count. So the way I've written it for number 4 is not, or for the 4 sig figs is actually not true. So how can I modify this? Maybe using our tool of scientific notation to actually include 4 sig figs. How would you write this in scientific notation? Say again? 5.06. I'm actually going to put that zero, that zero right there, I'm going to put it here because if I just put 5.06 times 10 to the blank, I still only got 3 sig figs. So that zero there tells me that fourth one does matter, and that's going to be times 10 to the what? Fourth. So 1, 2, 3, 4. All right, and that's milliliters. So I know it's the exact same number because we all kind of understand how these numbers are manipulated to scientific notation. But when I write these 4 digits in the front, those are where my sig figs live in scientific notation. They live before the times blank to their 10 to the whatever. So this has 3 sig figs the way it's written. This has 4 sig figs the way it's written. So to record things appropriately, that's kind of what we have to do, is kind of reflect at the very end of our calculations, how many sig figs are here, how many should be here, and then round as needed. So scientific notation will come into play there. That's probably one of the weirder things we'll do, but I'm going to put into context, like, why are we actually doing this right now, okay? So next on your paper, it says rules for addition, subtraction, multiplication, and division. Go ahead and read that for me, and then let's look at the differences between those rules. So Will, what are you saying that's different between those two rules? Cassandra. Okay, so we have 2 differences in our rules. You're counting sig figs to kind of control your final answer when you're multiplying and dividing. And then when you're adding and subtracting, you're looking for the number of decimals to control your final answer. It's just basically how do you record your final answer after we've done some sort of math calculation with it. So multiplying and dividing, the way you kind of consider this is the weakest link. So the lowest number of sig figs is how you record your final answer. So if you have a number that's got 5 sig figs in it and you're multiplying it by a number with 2 sig figs, well, the 2 sig figs is your weakest link. So that's going to be how you finalize your answer, with just 2 sig figs. So think about a relay race. Who runs track? Anybody? Okay. So that would be me. I would be that person you pass me the baton, the slow one. Can I get down the road here? I'd hold up the whole group, and we'd have the slowest time. But weakest link, that's kind of how the whole team has to kind of be based on. Same thing with our calculation. The weakest link, the one with the lowest sig figs, the least accurate, is how we record our final answers. Because you can't say, oh yeah, man, I had 1 sig fig in that one, but I'm gonna record it to 5 sig figs. So that would be lying about how accurate you were. Similar story with addition and subtraction. The lowest number of decimal, like numbers after the decimal, is how you would record some things that were added or subtracted. Because the weakest link controls how accurate your final answer can be recorded. And so we know all the words to all about that base. I can't remember the rules, but we'll work on it because we'll be practicing a lot. So start that little section of your notes because you will actually have to use those now, okay? And this is basically the last thing for today, and we'll actually finish up practicing some words and concepts we're getting and such. So let's finish these together. Step 1, identify. Oh, pull out your calculator. If you don't have a calculator, pull out your phone right now because I need you guys to actually calculate to see how your calculator tells you the answer. And then that moment of reflection of how do I actually need to record this. So, adding, subtracting, multiplying, dividing. What are we doing here?
Dividing.
We are dividing. Plug that baby in your calculator. Alright, so give me the long version of your answer. I might calculate with you actually to keep us on the same track here. Isabella, what's your long version of the answer before we even consider manipulating it? 0.8724. Like crazy, like this, something like this?
Yeah.
Okay. Grams per milliliter. Ain't nobody got time to record that many digits, okay? So you need to consider your rules. This is this is dividing. So your rules for dividing means count number of significant figures. So looking back at the two measurements we had, this was the first measurement. How many sig figs are there? 11.075. How many sig figs? 5. Okay, so if you're doing your Atlantic and Pacific method in your head, that's 100% fine. 5 sig figs here. How many sig figs here? 3. Who's my weakest link? 3 sig figs rules this final answer. I need to round this huge number to 3 sig figs. So I'm going to look from the left and kind of go in. So this one counts, and that 2 counts. Does that 0 influence the 2? Nope, it's going to stay as is. None of the rest of that matters, except for the units at the end. So, boop, 0.872 grams per milliliter would be the best way to record that final answer. That's why we went through how do you count sig figs, how do you round, and then now the rules for doing our manipulations. Yes?
Did you not use times 10 to the 6?
No, because times 10 to the 6 would make that number like 80,000, 87,000 or something like that. So you need to use scientific notation if you can't manipulate your number as it is written. Because like, remember that last example we did? We were like, oh yeah, we put the 0 in the end. But when we recounted, it only had 3 sig figs, so that's why we had to implement that. Good question. All right, down to B. Multiply. Put in your calculator. I'm not expecting you to do this in your head. Let's go, Zach. What's your answer? Just long version first. 4,900 units squared. Thanks. All right, centimeters squared. So now that's our kind of our calculator answer. Then we go back. How many sig figs are in 140? Say again. 2 sig figs. Good, because that 0 is actually just a placeholder if you count from the Atlantic. This one has 2 sig figs over here as well. Weakest link is 2. How many sig figs are right now in my answer? 2. I am good. These 2 zeros here, when you do your Atlantic method, you see the decimal is absent. You start from the Atlantic, skip, skip. Those are the only 2 that matter. Those are the 2 sig figs there. So that actually just worked out beautifully for us. Next, C. Plug that thing in your calculator. Brandon, what you got?
42.78.
All right, so this is all added up, right? So we just recorded centimeters, not centimeters cubed. So that's our calculator answer. How many, or what do we count with, in terms of addition and subtraction? Everybody. Decimals. How many decimals are here? 1, 2, and 1. Who's our weakest link? 1 decimal should be recorded at the end. So we have to take this, look at the 7, we want the 7. Right, so we want the 42.7. But consider the next number. Does that 8 influence the 7? Yes. Round it. What do you get? 42.8 centimeters. Beautiful. So I know you're like, this is just math. But we have the significant figure kind of the rules that we have to consider. So I want you guys to tackle D through H with the person next to you. That's fine. I'll put the answers on the board to give you a chance to check yourself as well. might be in the middle of a problem. Jump to G for me. It's the only one I think that you might have a question about if you've kind of followed along pretty well with class today. So G gave you 50.0 centimeters times 2 centimeters. So you probably said 50 times 2 in your calculator is 100 centimeters cubed. How many sig figs should be recorded in G? I'm sorry, it's multiplied, so we're looking at sig figs, right? So that's why I'm looking at sig figs. How many sig figs should be recorded in G? 2. How do you write 100 with 2 sig figs? 10 is still only 1 sig fig. It's like 10 is only 1 sig fig. 1.0, good, because we have our 2 sig figs there, times 10 to the second centimeters cubed, or squared. So that right there is where our sig figs live in our scientific notation. It's before the multiply symbol. So good, 1.0 times 10 to the second. That's the only one I think that you'd have an issue with. Other than that, most of them were pretty achievable with our 3 sig figs from E up here, 2 sig figs from F, and so 21. The 3 didn't influence the 1 to be rounded at all. H and D both were additions, so you had to consider decimals. D, someone asked me, hey, I don't have any decimals here, right? There's no decimal point period, so that actually you do not record with anything following a decimal because there is no decimal. So it should have been 0.5, and then you round it up to 65, right? Yeah.
For F, can you explain what is not decimal?
Yes, because I can either put the decimal or not, and I still have 2 sig figs. So I can keep it like this, because of the 2 sig figs being my ruler here, my overall thought at the end. So if I put the 21 or 21 point, they both yield 2 sig figs, so that's why I didn't put it. But that one's a tomato example. You could put the decimal just fine. Okay, guys, so if you feel good about that, go ahead, pull out, if you have a phone, if you want to go grab a laptop. We have about 20 minutes left, not quite 20, but close. And that'll give you a chance to finish up Prom Set 3A in class. If you've already finished Prom Set 3A, then move on to tomorrow's homework, which is reading guide 1 and 2. Okay? So I'm going to give you a chance to wrap it up and give you a chance to ask any questions. I think that's probably the time that we need right now. At the very end, I'm going to show you something with density. It'll be a quick video. So I'll put a timer on for about 12 minutes right now to kind of see where we get to, where we are. Raise your hand if you have access to Problem Set 3A on your phone. If you don't, please go grab a laptop, or if you printed it, that's also fine.
That's usually the easier part. The always true, sometimes true, never true. And sometimes you need to look for that, so I tend to wait on those. Caleb, I'll be right back. Right there. No. I can pull this up for you as well. And just to give you a little guidance, if I were you and you want some help in class, I would start on like number 4, because that's probably the stuff that we just did that you probably want to just really solidify in your mind. And number 5 with the rounding. The rounding is probably the iffy part. So I'd start there if I were you.
if it were like 0.507, there's like 5. All right, thanks.
Centimeter squared for C. Because it's a power that's supposed to work.
So what's your rule for multiplications? Yeah, so choosing reasonable. So what's your answer correctly? So that includes, and you just need two different, and so choosing the you can't put 25 for free. It's like too much. So you put 25, and then the rest of these will be plus 0, so you don't do this anymore. Not the multiplication. So the I noticed not only did that before, but you
So on C, I just want to know what would be the unit of compression?
so centimeters cubed divided by
So
centimeters.
the centimeter squared?
So finish the one you're on. We're going to do a couple more of these. Keep doing what you're doing. I wanted to kind of keep me in the loop what's how it was.
Is that right?
Will you check that for me?
I got
And make sure I record my right number.
I got like this big old number. I got this. I got this, but it has to be 3 sequence. Right? It's like 10 to 30, so.
Alright, eyes up here fast. If you're in the middle of a problem, I'm sorry. Work with me here. I'm going to show you one more example with scientific notation involved, and then we'll just watch a video on density at the end of class to kind of give you some heads up of we're doing a density lab tomorrow, where it's very close to our cheese, and we'll do some examples with this tomorrow. I don't feel like we should knock that out today at all. So we got, this is a 4H, I believe. So you see the scientific notation, you see it, you know that you're multiplying, you count sig figs. I kind of look at that at the beginning actually. You see there are 2 sig figs here, and how many here? 3 sig figs. So you know that in the end, 3 sig figs will kind of rule your final answer. I mean, 2 sig figs will rule your final answer. When you plug in your calculator, you get a humongous number. How many sig figs are in my numbers so far? 3, because there's no decimal. Those zeros are just placeholders to tell you the scale of this number is ginormous. So how do I write this in the easiest, fastest way to the perfect sig figs? Go for it, Frank. 1.4 times 10 to the 9th, because I ain't got time to write that many zeros. And you know what? We're probably going to miss a zero if you write like 7 zeros out. I did to begin with. So don't waste your time writing out huge numbers as zeros. Use your scientific notation. It's a cheap way of getting it done fast. So if I put the decimal there, that's 3.4, because I can only have 2 sig figs, so the 5 does round that 3 up to 4. And so that's going to be a 0 from there on out. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I wanted to actually include my units, what would I put here? It's just kilometers times kilometers, right? So that's kilometers squared. Perfect. Beautiful. Okay. So in terms of practicing, I know I'm probably going to be going over the rounding one with you guys tomorrow. Do practice with that though, okay? So we have a couple minutes left in class. I have a 5-minute video for you. I want you to jot down the ideas that they note. They're going to mention 5 facts about density, and you can write that down in your notes from today, wherever else you deem fit. So you probably know a little bit about density, but it's not quite 5 minutes. This will give you some more information.
A can of Diet Coke.
Some of them are interesting, so pay attention, people.
A can of Diet Coke will float, and a can of regular cola will sink when placed in water. You see, in the same amount of fluid ounces, there are more atoms in the can of regular cola. The main ingredients in cola are carbonated water and sugar. So each can has the same amount of water molecules, but in the same space, the regular cola has additional molecules from the sugar. Putting more atoms in the water forces the molecules to be more dense, making the cola sink.
All right, so more stuff in a specific volume meant the density increased. Does anybody know what densities actually, what its units are? Go for it, Brandon. Grams per milliliter, grams per liter even. So it's grams per space. So that makes sense. More stuff, more mass in there, density is higher, causes it to sink.
Hot air balloons fly because of density. Just like all matter, air is made up of atoms and molecules. When air inside the balloon is heated, it expands or gets bigger. So compared to the air around the balloon, the atoms inside have more room to move around and as a result are not as tightly packed together. The air inside the balloon is less dense than the surrounding air, and the balloon becomes buoyant. When it's time to land, the pilot stops heating the air, and as it cools, it contracts to match the density of the surrounding air. The effects of gravity go to work and bring the balloon down to Earth.
So this one talks a little bit how temperature can influence density, only really of a gas though, because you can expand the gas's volume, which causes a change in density. So temperature influences density.
If an object is cut in half, its density remains the same. Take a look at a gold coin, made of neatly arranged gold atoms. When cut in half, the tightness of the atoms does not change. Whether you have a half of a coin or a complete gold coin, the density stays the same. The density of liquid water is 1. Objects with a density of less than 1 will float, and objects with a density greater than 1 will sink. Take a look.
So what's the density of water?
1 what? Units. Grams per milliliter. Okay, that's 1 gram per 1 milliliter. That's the density of water. I'll come back to the other one we just skipped in a second.
And so you're talking about how can you determine
At these 3
buoyancy.
objects, all of them float, so their densities are less than 1. But if you take a closer look, you see that as density increases, more of the block is below the waterline. Scientists have figured out the density of a block converted to a percentage is equal to the amount below the waterline. For example, if 75% of a block is below the waterline, its density is 0.75.
and that would be interesting with especially like boats and ships and thinking about how can you keep it buoyant but submerged in the water so it doesn't just like tip top over top the water.
Ice floats because of density. When water freezes, it expands. Just like the expanding air in the hot air balloon, water molecules in expanding ice spread further apart. The atoms in ice are not as tightly packed together as they are in the liquid phase. If we observe an iceberg, notice about 92% of the iceberg is below the waterline. This means that the density of ice is 0.92.
And that's interesting because that's probably one of the only substances that when it freezes, it gets less dense. Most things when they freeze, they really tightly compact and they sink. They're more dense than a normal liquid form. Ice is a weird one. Water is a weird thing and it has interesting properties. So that's just a taste of density for you. Specifically, I want you to understand that density is a derived unit of grams per milliliter. So if you didn't get anything else out of that, you better have gotten that. So homework for tonight, finish up problem set 3A. We already did all the lecture notes. We did an awesome class today. I may have moved some maybe quickly for some of you, but I got some coffee at the end, so I was pretty happy with that. The nanotech project part 2, I gave you a yay or nay on your Excel file you did on Google Sheets. So you check that out. If I ask for any clarity, then you guys can clarify that for me. So other than that, I just think it'll look fine. It's not due till February the 6th, though. So, but I feel like you guys are able to move on with your problem set 3A. So we're leaving in like 2 minutes, 1 minute. You guys want to go ahead and put your laptops up? And then make sure the orange sheets are out here for me. You guys have a couple minutes to chat with amongst yourselves.